In this screencast, we will discuss the concept of cascade control, how it's implemented, and discuss the block diagram for cascade control. So before we do this, we have to think about why we would want cascade control. The majority of all processes that are being controlled take advantage of feedback-only control because of the numerous advantages that it provides. Its robustness, its ability to measure the controlled variable and act, its ease of implementation, etc. However, there are a few major drawbacks to feedback control which makes it impractical for particular types of purposes. The first is the fact that perfect control cannot occur. This may or may not be of huge concern, but it does work out more conveniently if you can develop a process where, for a particular disturbance, it can handle the disturbance such that the controlled variable is not changed. The second issue is that predictive control does not occur with the feedback-only scheme. Why? Because remember what feedback control does. Feedback control only deals with measurements of the controlled variable. So therefore, even if we knew something was going to happen, like we knew that there was going to be a flow rate change somewhere in the process, a temperature change, a pressure change, something along those lines, the feedback control scheme will not be able to handle that until there is a deviation in the value of the controlled variable. So therefore, for processes which have heavy disturbances, having a feedback-only scheme may have some problems. And related to that is for processes which are very slow or have large dead times, they don't necessarily handle disturbance as well because of that slow time to respond. So a disturbance will happen, but because of the large dead time of the process or large tau value, the time constant of the process, it will not be able to handle disturbances in a very efficient, quick manner, leaving the process away from its steady state for a lengthy period of time. So cascade control cannot provide perfect control. We'll discuss why a little bit later on. However, it can help with both predictive control and speeding up the process. Both of those two are directly related to each other. So cascade control can best be approximated as the idea of feedback control loops in series. And to exemplify this, we have a jacket reactor on the diagram where the desired variable to control here is the temperature inside the reactor. So this is our controlled variable. And the reason why you'd want to control temperature in a reactor would be that it can be useful to prevent runaway reactions. It can also be a nice way to, based on doing a mass balance on the system, know what your products are going to be, so therefore to get your system at its desired output. You have to set a particular temperature because temperature dictates reaction rate. So in this control scheme, the manipulated variable is going to be the flow rate of coolant to the system. Obviously, there's a whole host of other ways in which this could be manipulated, but for the sake of what we're doing here, it's the flow rate of the coolant. The temperature controller does not directly connect to the valve. There is a second layer here where the temperature controller sends its signal to a flow controller. And then the flow controller is also taking information from the flow rate of the coolant. So what it's measuring here is the coolant flow rate, and the flow controller is taking that information in addition to the information from the temperature controller in order to adjust the valve. So the temperature controller is represented as the primary controller. The primary controller in a cascade control scheme will always be the controller that corresponds to the controlled variable, in this case the reactor temperature. And the flow controller is the secondary controller, primary, secondary. There can be more than 2 layers of cascade control, so it can be ternary, quaternary, etc. Whatever is lowest in the hierarchy is the one that will directly control the valve. So some important information about the secondary control. There are 2 things that need to be the case in order for this to be a useful cascade control scheme. The first is the variable must fluctuate, and it must be a non-negligible fluctuation. Why? Because if the variable doesn't fluctuate, then the extra information being provided to the process is not useful. Additionally, if the fluctuations are relatively small in scale, and small is in the eye of the beholder, then again, it really isn't going to help improve this process. The second part is, remember that the whole idea of cascade control, if we look at the disadvantages of feedback control, is to speed up the process response. So therefore, the secondary control loop must have a faster response than the primary loop. A rule of thumb here is about 3 times faster, where this 3 times can come from doing some time analysis of the tau value, the time constant. If it's a little less than 3 times, what the issue is the fact that you now have this counterbalancing between, yes, you're quickening your response, but you've now also introduced new equipment, which can have fluctuations or which can break. So therefore, in terms of what is the net gain to the controllers overall, it may not be as much as you think. To go back to the issue of why perfect control cannot occur here, the reason why perfect control can't occur here is that there is still a connection here to the primary variable. So in other words, the secondary variable's decision-making process is based on what is going on with the primary variable. So therefore, it helps mitigate the idea of the possibility of perfect control. So what we'll do here is kind of talk about the loop in a bit more detail.